All right, party people, let's talk about oxidation states. This idea really isn't that foreign as they're related to the charges that we saw when we worked with ions. The term oxidation state is a bit more broad than the term charge and can be applied to atoms and molecules as well as atoms in ionic compounds. Try to look for the similarities to what you already know as you work through this material. In the nomenclature module, we use the term charge. Doing so meant that we were talking about the actual electrical charge on an ion. And we were correct to do so there because the transfer of electrons and ions is a permanent change, which means that charge we referred to is also an actual value based on the number of protons and electrons in that ion. That count gets us to something specific and constant. Now we're going to switch gears a little when we talk about oxidation states, a term that describes the hypothetical charge an atom would have if it were part of a fully ionic bond, which obviously isn't a thing in molecules or polyatomic ions that come from molecules, which are defined as having shared electrons. The oxidation state becomes more important with complicated species, but even in simpler ones, it's a useful bookkeeping tool to help keep track of what things have fewer electrons and what things have more electrons. Think back to the partial charges you saw on a water molecule earlier. The oxidation state also helps us keep track of electron movement. I'll try to illustrate the difference between charge and oxidation state with the calcium ion. We know that it is a group 2 metal, and as such it should form 2+ cations. Losing 2 electrons gives the calcium ion a charge of exactly 2+ based on the proton and electron count. We write this with the numerical value that matches the magnitude of the charge first, followed by the sign on that charge. This is 2+ for our calcium ion. Oxidation states, in contrast, are given a slightly different symbolism so that the two concepts aren't confused. We will report oxidation states by first stating whether the element's predicted to have more electrons around it, do this with a minus sign, or it's predicted to have less electrons around it, do this with a plus sign. You follow that sign with either a standard or a Roman numeral that denotes the actual charge on the atom or ion. For calcium, that looks like +2 or +2. The old guard is probably more likely to use the Roman numerals because we're old. This should look familiar though, as it was the method we used for naming variable oxidation state transition metal cations in section N.2. There are a lot of things to keep in mind when determining the oxidation state of a compound. Your first job is going to be to work through a table of common oxidation states given in the content page so that you can better solve for an unknown, and to remember that compounds are neutral species. 3 big highlights are all of your elements are going to be considered neutral, so they will have an oxidation state of 0. The oxidation state of any monatomic ion will be equal to the charge on that ion. You can think of an oxidation state interchangeably with the charge when you're dealing with ions. Just watch out for the formatting on which one you're supposed to report. As a reminder, the calcium ion we just saw is a monatomic ion. Lastly, if you are asked to find the oxidation state of an atom that's part of a polyatomic ion, you'll need to take the charge on that entire ion into account when determining that missing piece. Remember that your polyatomic ions are formed from molecules, so charge and oxidation state are not interchangeable here. Covalently bonded things won't have a charge, but they will share their electrons unevenly a lot of the times, so they will have a predicted oxidation state. We'll practice determining oxidation states in a later video, but just as a reminder from section N.2, if you need to find the oxidation state of something that's part of a neutral compound, your expression will need to be set equal to 0 to show that neutrality. The example shown here involves determining the oxidation state for the iron in iron 3 chloride. In contrast, if you need to determine the oxidation state of an atom that's part of a polyatomic ion, you would set that expression equal to the charge on the ion. Here, I've determined the oxidation state for the phosphorus in the phosphite anion. Note that the charge on the polyatomic ion is absolute and permanent, and my notation denotes this with the 3-. The oxidation state on the phosphorus, however, is not absolute and permanent, so the term charge is no longer appropriate, and I've denoted this with my notation. Same with the oxidation state of the oxygen that I used in the calculation. It's important to understand that your atom doesn't know how to calculate oxidation states. This is a human construct that we are imposing on our atoms and molecules. It's actually fairly unlikely that all the oxygen atoms in this phosphite have a consistent -2 oxidation state, while the phosphorus has an unfallible +3 oxidation state. If that's the case, why do we even care? Well, for one, determining the oxidation state lets us see where we might have more electron density. Since the oxygen atoms have a negative oxidation state, they're more likely to carry that electron density with them than the phosphorus is. For another point, and this is a very key point for our particular section, if we predict what the oxidation state of an atom is before and after a reaction, we can determine if the electrons were transferred as part of that process. We will always use these idealized oxidation states when following electrons in our oxidation reduction reactions.